if we looked into the new section, we're going to look at acids, bases, or acids and bases, and then some equilibrium concepts, and that's pretty much it. Okay? So if we went through to name each of these compounds, we'd have to go through and evaluate what components were present, and then try and break that down and classify it into the correct category for each of those names. Technically, the middle one becomes a little bit tricky because it doesn't quite fit in any of our categories. Okay? But the first two should not get named acids for this class. Why is that? It needs to have the AQ after it. Okay? It's a horrible definition, but that's what we're working with. Okay? The last one would get named sulfuric acid because it's a complex ion, and we have to follow all of those rules for nomenclature. Okay? So why does sulfuric acid get a different name? Okay, why do I have to add that acid part of it? Okay, and this kind of comes back to historical aspects. Your acids and bases were initially discovered very early on. So we had observations made about some of the chemical properties. Okay, and they noticed that some materials could melt your face. Right? Hence the sticky feeling, because as it's melting your face, you can feel your face like stick. Okay? Same with your hands if we wanted to get less graphic. Okay? We could also go through and taste them, and they tend to taste it kind of sour. So they had some observations about these chemicals. Okay? I also noticed there was another class of chemicals that were bitter tasting, and they had kind of a slippery feel to them. When I mixed them, they reacted rather violently with each other and generated lots of heat. Okay? So we had some just kind of observations about these. Because these chemicals were pretty readily available, or sort of readily available, easier to isolate, we could then categorize these as our initial definitions for chemical reactions. And that's where we have acids and bases. So acids and bases is probably the oldest and most common type of chemical reaction that you deal with in general chemistry because it just happens super frequently. And if you ask a little kid, do you want acid splashed on you, they tend to know that the answer is no. Okay? So we've trained that in very early on about the dangers of our acids and bases. Lots of chemicals have dangers. Acids tend to be higher up, okay, in that ranking. Right? So chemists later went through and noted that those sour-tasting, sticky-feeling compounds we're now going to call a particular name. And we could call it anything we wanted, but what we called it was an acid. Okay? So our sour-tasting and sticky-feeling were all classified as acids. So in this case, if we added the AQ on that, we have acetic acid. Right? So you know how to name that. The other compounds were all classified as bases, right? Or what we've now called bases. And they were bitter tasting and slippery feeling. Right? And it turns out that what we could then look at would be, say, something like sodium hydroxide, and that is now a stereotypical base. Okay? So what we wanted to do is now come up with definitions that would help these. So I could look at a structure provided on, say, a label and say, well, that's going to act as a base or an acid. But we've got it for acids. We don't necessarily have it for bases. Because the only other way to test this would be to, I don't know, taste it. Probably not a good idea. Okay? Anybody know a common base that you probably used this morning? Soap. Soap is a base. So if you ever had parents that would wash your mouth out with soap after you cursed, you might recognize the bitter taste. Soap is a base. That bitter taste that you're getting is from the base compounds of your soap. The slippery feeling is allegedly, though I'm not quite sure I believe it, is that it's reacting with your skin and turning the fats and oils on your skin into soap molecules, which is why it becomes slippery in your fingers. When you react a strong base with your skin, you're literally making soap out of your body. Generally not a good idea. Okay? So the definitions that came along after this, one of the oldest one is named after Arrhenius. Okay, and he went through and noted that when we took an acid and we added it to water, that there was an increase in hydrogen ions. Okay, so our hydrogen ion is that H+. So any species that I add to water and H+ concentration goes up is now defined as an acid. Okay? That's a better definition than what we've been working with, because we just said for it to be an acid, it has to have the H and it has to have AQ. Okay? His definition isn't that much better, okay, but it's not too far off. Okay? We have to have H, because the hydrogen ion must go up, and we must have AQ. Well, where does the AQ come from? What does AQ mean? It's aqueous. What does aqueous mean? Literally dissolved in water. So the Arrhenius definition is pretty much following off of what we've learned to name our acids. We have hydrogen and we have aqueous solutions. And in particular, that hydrogen must break away from the structure. Okay, so we could now change the format of our structures to address something. Okay, so for instance, if we looked at acetic acid, we would typically reference it in this fashion, okay, with the H out in front. Now I don't have to include the H out in front. I could go through and put it in the middle. That now hides the fact that it's an acid, but if I know when I add it to water I see H+, now what do I know? Well, now I know that species was an acid. Okay? So if I've got some of that reaction context, I can apply it a little bit better. It's still a very narrow definition, but it works okay. What happens when we move to bases? Okay, well, bases need to supply something to react with that H+. Well, what charge might you expect to be attracted to H+? A negative. Right? What charge is hydroxide? A negative. Okay, so when we're looking at our acids and bases, we're really just looking at how these charges would assimilate or attract to each other. And we get hydroxide being attracted to the H+. So now my definition for a base is anything that produces hydroxide when added to water. Interesting feature behind all of this. Let's take water. What could I break water into? H2O is the formula. What could I break water into? Not to give away too many hints here. H+ and OH-. Okay. Water is consumed, or made from, not consumed, is composed of both H+ and OH-. When we change the concentrations of H+ and OH in an aqueous environment, what we're really concerned about is how is the balance of that secondary reaction, the one at the bottom, how is that one getting affected? So what we're talking about is bases and acids messing with those concentrations, which then ultimately messes with how that reaction works. Okay? So the fun thing about these definitions, okay, and I have since softened my opinion on this a little bit, I tend to consider these definitions really, really useless. Okay? And the reason being is that they only work in water. Okay? Well, when might you have a reaction in water? What phase have you used for all of your reactions in lab? You haven't used liquid. Well, you sort of used liquid. It's been water. Everything you've done in lab has been dissolved in water. Okay, why water? It's super cheap. It's super common. It's in a liquid state. We don't have to change the temperature to get it into that liquid state, so it allows us to mix these things pretty well. Okay? So that's one of the reasons why we use water. So most of what you see in general chemistry is water-based. So these definitions technically aren't useless. They're pretty good for almost everything you would do in general chemistry. Why might I consider them useless? I was hired not to teach general chemistry, but to teach Organic chemistry. And in organic chemistry, we rarely use water. Why? Because it generates acids and bases, and I don't want those acids and bases present in most of my solutions. Okay? I want to run other reactions. So water tends to not be a common thing used in organic chemistry because it can mess with my reactions as both an acid and as a base. Okay? So I tend to see that as useless. If water's not present, I can't use these definitions of acids and bases because I'll still have acids and bases present in solution. Yeah? The Arrhenius definition could easily be on the exam. Okay? As history progressed, we went through and tried to adapt these rules and make them a little bit broader. Okay? For instance, if we looked at, actually those reactions weren't the greatest. If we scaled out to other reactions, say like NaNH2, if I add that to water or dissociate it into the ions, I'd see sodium ion and NH2 minus. Do we see hydroxide? No. So I say, well, that's not a base. Okay? This is a stronger base than hydroxide. Okay? This one is pretty much instant death. Hydroxide would just be slow and agonizing. Okay? So I need a definition that would encompass and allow me to appropriately classify that compound. That's where Bronsted-Lowry came in with a slightly new definition. And instead of referencing acids and bases as two separate independent things, acids being H plus and hydroxides being bases, is he went through and said, well, let's just pick one of those definitions and let's stick to that one definition. H plus as an acid turns out to not be all that bad of a definition. So when he went through and looked at our acid definition, he referenced it as a hydrogen ion donor. Okay? And instead of labeling bases as hydroxide ion donors, he referenced what the base is doing. Well, it's reacting with the acid. Well, what is the acid giving up? Hydrogen ion. So what must the base be doing? Accepting it. So we change the definition ever so slightly. This doesn't change the meaning of our acids and bases. I could still go through and take an acid, HCl, and react that with sodium hydroxide. Sodium hydroxide still fits in our base definition for both Arrhenius and technically Bronsted-Lowry. Why? What happens? What's the result of this? I get H and OH plus sodium chloride. What can you tell me about sodium? Never mind, ignore that question. If we now go through and look, what did the base do? So what is the reactive part of the base? The sodium or the hydroxide? Okay, for those of you saying sodium, okay, our base is dangerous. Bases are just as dangerous as acids, they just do a different reaction. Okay, so bases are dangerous. Are we particularly concerned about sodium ion? Okay, this class has probably already shed enough of these, but let's say the final rolls around. After the final, we may get tears. What are we crying out? Sodium ions. Is our face melting off? No. Is the sodium ion the toxic thing? No, it's the hydroxide. The hydroxide is what makes this a base. What did the hydroxide do in the course of this reaction? Well, here it starts as hydroxide. What ended? What happened to it? What changed about its structure? Say that again? It picked up hydrogen. So what did the base do in the course of the reaction? It accepted a hydrogen ion. Right? It still supplies the hydroxide, so it matches the Arrhenius definition, but it now also fits under Bronsted-Lowry. Well, why do I need Bronsted-Lowry? Do I have to have sodium hydroxide? No, I could have just had NH3. Well, what happens with NH3? Well, NH3 can pick up that hydrogen to form, what is this species? Name that compound. That is ammonium ion. Did you see hydroxide in NH3? Do we see OH? No. Okay, there's no OH there. Yet what did NH3 do in the course of this reaction? Look at the products. What happened to the NH3? What's connected to it? It accepted a hydrogen. So according to the Arrhenius definition, NH3 is nothing. Doesn't fit acids or bases. But what did it do? It accepted a hydrogen. What is Bronsted-Lowry's definition? It accepts hydrogen. NH3 is acting as a base. So Bronsted-Lowry's definition now expands the realm of chemistry so that we can better classify our compounds. Well, why do we want to classify our compounds? Right. Well, we have good and bad guys, right? Is it useful to classify good and bad guys? No, it's not useful at all. Okay. So like the murderers, the rapists, the father stabbers, the mother stabbers, those people we don't want to classify. We just want them out in the population in general. It's like, yeah, hell yeah, bring them out. We classify them. Why do we classify them? Because they're going to hurt us. So we classify and try and establish those relationships so that we can better interact with the world around us. I want to be able to classify all of my chemical compounds so that I can look at it and be like, I don't want that on my skin because I'm going to die. Okay? So I need the ability to classify my compounds. This is where the definitions of acids and bases are ultimately coming from. It allows me to classify them and potentially store them in different locations. Okay, which brings up the next kind of point behind this. Acids and bases react with each other. If they react with each other, they release tons of energy. If I store an acid next to a base, and say an earthquake happens and the containers break, well, when the acid mixes with the base, it generates a reaction that produces lots of heat. So now not only do I have an earthquake causing things to break, but I now have a chemical reaction that's releasing tons of energy. And if I'm in that same room, I could potentially get seriously hurt. Not just from stuff falling off the shelves, but now a chemical reaction as well, or chemical burns. Okay? Because I've got this classification system, what does that mean I should do? Store the acids and bases in different locations. This way, when they break, they only mix with other bases. Not a big deal. Or when they break, they only mix with other acids. Right? Yes, that's going to be a chemical hazard, but that's now a smaller chemical hazard than it now also being a heat issue, okay, or a potential burn. So by classifying the compounds, I can organize where they're located with respect to each other and improve my safety and longevity as a human being, okay, which may not be the greatest sometimes, but.
You know that's right.
Okay. This is one of the reasons why if you look at the lifespan for chemists, they average 10 to 15 years less than the standard population. Why? Because we're still figuring stuff out and making sure things aren't stored next to each other. How do we find out that it was a bad idea to store those two things?
The hard way.
Usually the hard way. They mix by accident, they cause an explosion, and we get hurt. That's why chemists end up living less. Right? It's an exposure hazard. If we can better classify our reactions, the better we're set up to organize and keep ourselves safe in the process of learning new material. Okay? So, if we take a look at these two chemical reactions, they are related to each other. Right? So let's take a look at the top one because the top one's the easiest. Right? If we look at those two compounds, I want to be able to decide which one's an acid and which one's a base. Right? Well, what did we say an acid needed to be? Hydrogen ion Donor. So what should the acid have in its formula? Hydrogen. Can SO3 minus 2 act as an acid? No, because it doesn't have hydrogen, which means H3O plus is going to act as our acid, and SO3 minus 2 will act as the base. The acid donates H plus. The base must accept H plus. What does the base need to react with the H plus? A much harder question. What is that?
Negative charge.
Why are you saying a negative charge? And I don't know.
Just in case we were.
That's fine. Why did you say negative charge? The hydrogen is positive. What is attracted to positives? Negatives. What does the base need to have? Negative. What does SO3 minus 2 have? Negative. Okay. So if we can use those definitions and apply them, we can come through and say that this SO3 has to have some kind of negative charge to act as a base. So very quickly, looking at a compound, I can say that can act as a base, that can act as an acid, by applying those definitions out to our structures. For those of you who have to move up into organic chemistry, that is literally what you need to do. We spend a semester and a half fighting with negatives and positives because you don't believe that's what you need to do. That is literally organic chemistry. Find a negative, find a positive, and put them together. That's it. Okay? All that happens in Gen Chem is all this numerical stuff that then confuses that issue. Negative, positive, put them together. Okay? So the acid needs to give up H+. So if H3O plus loses a hydrogen, what would its formula become?
Wait, say that again?
If H3O plus loses a hydrogen, what does it become? It would become H2O. What should the charge be on that? Why no charge? H3O was positive. If I get rid of a hydrogen, it becomes H2. Why do I no longer become positive? Because what did I get rid of? The positive charge. So it becomes H2O. Right? What happens to the other structure? Where did that hydrogen go? It went to the base. Fair answer, because no one knows that that's sulfite. That's good. Okay. So we would have SO3, right? But now we have a hydrogen attached to it, HSO3. What should the charge be on that structure? Why are you saying negative, Bev? What charge did the SO3 start? It was -2. What did it just accept? A positive charge. Should it be -2 anymore? No. One of those negatives is canceled by the positive. All right. What happened to the other one? It stayed. I didn't do anything to it. Okay. Theoretically, yet. And this is where acids and bases, as reactions, bring in a new kind of level behind this. We're only running one acid-base reaction, which means what do we end with? Charged structures. Okay? That charged structure is new to you because whenever we ran general chemistry reactions before, what was the charge on all of our products? 0. Okay? When we're running an acid-base reaction, we're defining it as a single step first. And if we want to do more, we can potentially, but we want to start at a single step and keep it simple. Right? This does mean we could produce charged structures. Right? So that's our first reaction. Does anybody notice anything interesting or different about that reaction beyond the charges? The arrows, what do you mean the arrows? Yeah, when we looked at our chemical reactions before, what kind of arrow did we have in between? A single arrow going left to right. Because how do reactions work? We have reactants on the left side of our arrow, and on the right side of the arrow we have products. Right? Turns out that's not true. Right? All chemical reactions will go both left to right and right to left. There's always this double arrow in between. It just so happens that what we've talked about so far this semester, that arrow for the reverse reaction tends to be so small that we ignore it. Okay? It is still present, though. Okay? So now we're bringing in that arrow. So what does that then mean for this reaction? What is on the right-hand side of the arrow now? Okay, or said again, on the left-hand side of the arrow we had reactants, on the right-hand side we had products. If I now acknowledge that I also have that arrow, I have reactants where? On the right-hand side, and I have products on the left. Okay, I'm going back and forth between these, which means if I now read this right to left, what has to happen to H2O to become H3O plus? It had to accept a hydrogen. What species accept hydrogens? Bases. So guess what H2O is? It's a base. Okay. What is the HSO3 minus? What does it have to do to look like SO3 minus 2? It needs to donate that hydrogen to something else, which means HSO3 minus is acting as an acid. Okay. So we're putting in those labels based off the definitions as we understand them and working with them. Does that make sense? So now let's ask a test question. Given that chemical reaction, which one's the acid? Okay, we don't have sulfuric acid. We technically have HSO3 minus or hydrogen sulfite. Okay, so I'm hearing a vote that the acid is this guy. Does everybody agree? That's the acid. No questions. Okay, you're shaking your head, Z. Why?
Because on the left side, the acid is also the H.
On the left-hand side, I've labeled that an acid. So this now becomes very confusing. Which one is the acid? Well, the one that's the reactant is. What did the double arrow mean? Which means both of those answers are reactants. So which one's the acid? Okay. So one statement, neither one says aqueous, but remember what we shifted away from on the previous slide. Hydrogen ion donor, hydrogen ion acceptor. There's no mention to aqueous or not. So how would we define? This now becomes tricky because we have two acids. How do we know which one's which? Right? So what we tried to do is invent a term to allow us to explain which one's which. Okay? Organic chemists seem to be pretty consistent on this. General chemists seem to not be. Okay? This side of the reaction is now my absolute reactant side. So I will define those as bases and acids. The product side are also acids and bases, but I want to add a new term so that I know I'm referencing those as products and not as the original acid and base. So what I will add to that is conjugate. So the conjugate acids and bases are always on the right-hand side of the arrow. Your acids and bases are always on the left-hand side of the arrow. Now when I ask the question, which one's the acid? It's the left-hand side, it's H3O+. If I ask for the conjugate base, what's your answer? H2O. This allows for a more clear explanation on which piece is which, right? That helps us go through and define these. Well, what is conjugate in reference to? The only example I've got for other words that could apply to this is not the most appropriate, but it's all I got. Conjugal visits. Okay. What's the deal with our conjugal visits? Someone's in jail, and a spouse or partner is allowed to visit. You have to be a spouse. Intimately. So there is a relationship established for a conjugal visit. This conjugate base applies intimately to which of my starting materials? The conjugate base, H2O, looks most like which of the starting materials? H3O. These two, H3O and H2O, are conjugate partners. H3O plus is the acid, H2O is the conjugate base. What's the conjugate partner for the SO3 minus 2? The HSO3 minus. Those are now conjugate partners. Right? So if I can reference these, it allows me to better define those relationships, and I can now tie what happens to them through the course of the reaction. What happens to the acid in the course of a reaction? What does it become? Becomes a base, and it becomes the conjugate base because we're saying what happens to its ultimate structure. Because when we reference the reversed reaction, it has to act as a base. So your acid will never be the conjugate partner of another acid, because then it didn't act as an acid to begin with. Right? Across the reaction, they must change. Kind of make sense? Okay. So we could go through, I've got a million steps through this. Okay. We could go through and look at the bottom one. What makes this bottom one trickier than the top one? Nothing makes it trickier. It's exactly the same. How do you know you have an acid? It has to have an H. What's this first one have?
H.
What's the second one have? H. Why is this one difficult? Because they could both act like acids. Right? So it becomes a trickier question to deal with. What we're looking at is substances that are amphoteric. They can act as both acids and as bases. Some compounds have that ability, some do not. We just kind of have to be aware of them when they come through. Right? So in this case, I just happened to decide the HSO3 minus acted as the acid. You could go through, see those partners, what happened with those structures. But that's probably more work than we need to do. So there's our answers on those. Okay. I now want to really address what's going on with that double-headed arrow. Okay. Because that double-headed arrow is what is known as the equilibrium arrow. Okay. For future reference, if you have to move into a general chemistry class, if anybody goes through and tells you that this arrow, okay, right up there, now in that box, that red arrow is an equilibrium arrow, you can tell them flat out they are wrong. Okay? And if they're like, no, it is, you can tell them to email me or contact me, and I will tell them on multiple occasions that they are wrong and they need to stop using that as an equilibrium arrow. Because that is not an equilibrium arrow. Okay? That arrow is applied only for resonance in organic chemistry. That is the only time you use that arrow. You will never see that arrow unless you move into OChem. Okay? So, we look at that reaction. What we're talking about is reversible reactions. What's known here is an equilibrium. It turns out that what our reactions will do is find a balance between reactants and products. Okay? Where that balance is dependent on the reaction itself. So every reaction has a different balance. But all reactions are attempting to achieve that balance. Okay? This is why when we mix an acid and a base, they're like, oh crap, we're not in balance, and they react very, very quickly to produce products, to become into balance. Okay? And in particular, their balance. Okay? This observation was made for LeChatlier, okay? Which I guess is a French person, because that sounds kind of French. Okay? And what he pretty much observed was that all reactions are going to do whatever it takes to achieve balance. That balance is our equilibrium. Once our reactions are at balance, okay, that doesn't mean they stop. They're actually still reacting. Okay? But the rate at which they react is now equal. So the rate for the forward reaction and the rate for the reverse equal the same thing. Which is a confusing concept, so I won't stress too much yet. We'll look at some pictures for it. Okay? And what he went through and did is said, okay, well now let's look at a reaction that is at this balance. What happens if I mess with it? Okay? For instance, if you're standing still and balanced, and someone comes along and pushes you, okay? Well, what do you try and do? You try and re-achieve that balance. If you didn't try that, what happens? You fall. Okay, so everybody tries to re-achieve that balance. As we walk, we're shifting our balance. We're going out of balance and re-obtaining that balance as we move through. Okay, so that we're in a constant oscillation to make sure we stay static at a balance. Chemistry is doing the same thing. The fun part is that chemists can come along like obnoxious robot people, scientists, and push and see what happens. Okay, so if you've seen those videos with the scary robot in, was it Boston Dynamics? If you haven't, you can go check them out. They've created a robot now that can walk and self-sustain and all that. And they can kick it and throw it on the ground and it re-achieves its balance and gets back up. Okay? That's what's happening. That's what LeChatlier effectively did, but to chemicals, not to a nice little robot. Okay? So we're messing with the reaction and seeing what it does to re-achieve that balance. That process is ultimately now shuttling and either making more products or making more reactants. That's how it achieves that balance. Okay? As a chemist, what would we probably try to do? Do we want it making more reactants or making more products? We probably want it making more products because... Okay. That's the whole point. It's like talking to a construction worker and saying, I've got all these pieces for you. Do you want me to make more pieces or should we turn it into a building? Probably like, you're an idiot. Don't give me more. Let's just turn it into a building. That's what chemists are doing. We're building buildings. Okay? So if I take a bunch of chemicals and put them together, those are my pieces. I want to turn that into something. I don't want to turn that something back into more pieces. That just means more stuff for me to clean up. Okay? So, here are some comparisons that we can look at. Right? The first one's a bit of an old school example because they started removing them from playgrounds. Seesaws. Right? If you've seen these, take the little seesaw in the middle. You can put a happy little kid sitting on that. It's got a little handle. You hold the handle. Put the other kid on this one. He's got a little handle. And they can jump up and down, right? And it bounces. Yay, it's fun. What?
Arms don't bend like arms broken, but they don't care. I bet that's wrist.
That's his wrist, yeah. That's his wrist.
Chris is out of the
So I'm hearing that a biologist wants to come up and draw this more appropriately.
Well, I can draw better than that, and I'm not an artist. So.
Did you understand what I was trying to draw? Yeah, then there you go. Okay. So chemistry is doing the same thing. Okay, so we go through and we want to achieve that balance. Okay, so if I start a reaction, all I'm going to do is take reactants and I'm going to put them on the seesaw. What happens to the seesaw? Is it in balance? I just put reactants on there? That's going to be balanced. What's going to happen? This is going to fall, right? That's not balanced. That's out of balance. I want that thing flat. So what does chemistry go through and do? How does it balance it? Makes what equal? It just goes through and says, oh, well, I'll put in more products. Did I change the reactants? This example, did I change it? No, I can't create matter out of thin air. What happens to make those products? I go through and I take some of the reactants and I turn those into products, which means that is now gone and it becomes a product. Now is it in balance? Ballpark. Yes. All right, now that I've achieved that balance, this is where LeChatlier says, okay, well, what happens if I go through and add more products? Is it in balance? No. So what does chemistry do? I need more reactants, but I can't create that matter. What do I have to do? I'm going to have to get rid of some of the products and turn them into reactants to get it to balance out. Right? So what's happening is I'm constantly shuttling between reactants and products, backwards and forwards, to make sure I've achieved this balance. Right? And again, we can't create or destroy matter. So all that's happening is we're now messing with the reaction. So one, I added more products. What if I added more reactants? Here's more reactants. Now what has to happen?
You gotta take some of that reactant.
I got to take some of that reactant, whoops, well, fine, away, and I have to turn it into products. The chemical reactions are literally just doing that. You could imagine it as the robot that's now shuttling stuff back and forth between those to make sure that they're even. One of the problems with this example is this now appears static. Right? Once we've achieved equilibrium, nothing happens. That's not true. It does continue to shuttle back and forth. Okay? And we'll look at that in a second. The other thing with this example is this now looks like I would have equal amounts of reactants and products. Right? But not necessarily. Okay? And in a real chem lab, that is an awful experiment. Because if I start with 5 grams and I have to make product, well, now the most product I could make would be 2.5 grams. That's a 50% recovery. That's not very good. How could I improve the yield? Right, well, what I would need to do is change the experiment. And remember, the balance is defined by that chemical reaction. So if I now change to a different chemical reaction, okay, the balance changes. Well, where's the balance in this reaction? What defines how much reactants and products I would need to achieve that balance? For those of you who have taken physics, this would be the answer. Where's the equilibrium? Where's the equilibrium in this example? It's the fulcrum. It's this little wedge. Okay? If I want an experiment to produce lots of product, what happens if I put the fulcrum right here? Okay. So now let's put in the reactants. I'd be out of whack, right? So how would I achieve the balance? What would need to happen? Well, I need to get rid of some of that reactant and convert it into product. So, right, equal amounts.
No,
Why not?
because that's not how physics works.
Fairly legitimate. Okay, it's not how physics works. How much product should I make?
You should make more.
Okay, what happens if I make more product?
No, just kidding.
On one side, you have to have less product.
I'd have to have less product. Okay, so what's happening is we're just saying, how do we cause this shift to occur? Okay, so really, whoops, that's not what I wanted to do. What do I want to do? I want a very tiny amount of product to be taken out. And that's going to be dictated based off of where that centerpiece is, that fulcrum. Kind of make sense? Right? So this would be a horrible chemical reaction to run, because what I'm doing is mixing all my reactants together and I'm getting nothing out of it. All I'm getting is the reactants, virtually a tiny amount of products. So this would be a horrible chemical reaction. If I knew where that equilibrium lay, I would decide that this was not a reaction I'd want to test. Okay? Where should the fulcrum be? How about if I put it right over here? Now what's going to happen? I'm going to have a very tiny amount of reactants, and I'll have a lot more products to counterbalance. So if I can establish that my equilibrium favors my product, that's going to be the better system. Make sense? Okay, so let's switch to the other example. We have two divided chambers. We'll call chamber 1 reactants, and we'll call chamber 2 products. Okay, it's equilibrium, so it can go backwards and forwards. When I start a chemical reaction, am I going to have any products? Probably not, because if I had the products, I probably wouldn't be doing the experiment. I have the products. Okay? So to start off, what I'm going to do is put up a little barrier, and I'm going to now fill chamber 1 with reactants. Okay? We're going to pretend that that is now a liquid. Okay? So in our analogy, that is just a liquid. Okay? I've got all my reactants set and ready to go, and now I say, magical reactants, do your thing. And in the process of doing so, what happens to the reactants? They need to become products. So I'll erase the barrier. Now what happens to the liquid in the reactant side? It would go down. At the same time, what's happening?
Product rises.
The product side rises until what happens?
They're both equal.
Until we end at the system where they're now both equal. I've now achieved my equilibrium. Okay? Once here, does reactant stop moving over to product? No. It will constantly move over. But at the same rate that the liquid moves over to the right chamber, what's happening?
Right moves to the left.
The right moves to the left. So this is a better representation of a chemical equilibrium. Our reaction is still running both forwards and backwards, but it's going at the exact same speed. So the result is I see no change in the overall amounts of reactants and products. Make sense? Okay. So now that I've achieved my equilibrium, I'll go through as LeChatlier and say, okay, reaction, stop. Stop doing what you're doing, and now I want to mess with you. Okay. So on the seesaw example, I added stuff. Well, this time I'm not going to add, I'm going to remove. I'm going to remove some reactant. Okay. Now that it's removed, I'll say, okay, reaction, do your stuff. What happens?
It'll still be balanced eventually because both the left and the product would go.
Eventually you would achieve balance by doing what?
Well, like you said earlier, the product itself would lower down, and then
This will drop, the reactant goes up until we've achieved a new equilibrium. Right? All chemical reactions are attempting to achieve that equilibrium. In this case, the amount of reactants and products is equal. How could I change my example to say I get more products?
Well, what do you need to build a barrier again? And then build the product itself.
Okay, so let's build the barrier. Okay, and I want to end now with more products than I had for reactants. What would I do? I said more products, so I'll put a bunch of products in, but no reactants. And now I say reaction start. What happens?
No, you have to add reactants.
I add reactants. Now what happens when I undo the barrier? Nothing happens. I'm at my equilibrium. I haven't obtained more product. If anything, I had to add more of both products and reactants. I want more products than reactants. What could I do to change this?
Wouldn't you just put the barrier back up and have more sugar reactants on? Or the product soda?
So one option is I could now add more. We need to drop that line a little bit. Okay. There was a suggestion of now adding more products in. What happens when I remove the barrier?
So equal, but
It still equals, and the product amount drops. So I end up with less product than I started with. So that didn't work. Right? What if I added more reactant? Now when I remove the barrier, yes, I'd get more product, but I still have an equal amount of products and reactants. It has to do with the barrier.
we still don't put them on the top or anything like that?
Then nothing happens and we still have an equal amount of both.
Not that. Yeah, I think so.
Right? Now what happens?
Yeah.
Now when I let the reaction go, the reactants flow across. Very small amount. If we end this, we attempted to do with the volume difference here. I would have a very small amount on the reactant side and a lot more on the product side. I get a better distribution, right? A more favorable one. Equilibrium is what's defining where that line sits, where the division between those two chambers is. Much the same as equilibrium defining where the fulcrum was in our seesaw. It's the same concept. Right? So when we're talking about equilibrium, those are being like, this is a difficult thing to explain and understand. That's true. Okay? It is very difficult. Literally all of second semester quantifies this. All we went through and did is say, well, what happens when the liquids shift back and forth? Well, now it'll be like, well, you have 50 milliliters of a 5.2 molar solution of this and 20 milliliters of a 3.6 molar solution of this. What happens? You would have to deal with those numerical analyses to try and decide what the relationship was. Okay, what was the end result? So it becomes a lot more quantification behind it, which makes it a lot more difficult. Okay? So before we even get into that, what things might affect the rate at which our reactions go? What's going to change that rate going backwards or forwards? Okay? So now what we're doing is not looking at equilibrium, we're going to look at kinetics, speed of a reaction. Right? Like, oh, God, reactions, I don't know anything about chemistry. Okay? Have you ever had a relationship? For those who are saying no, technically that statement was really, really, really vague. You've all had a relationship with me. Just because you're making the relationship at a different level, okay. Right? How did you get a relationship with me? You had to sign up for the class. You had to come to the class. Those two substances, those reactants, had to be in the same place. If you never came to class, would you ever establish a relationship with me? No. We want to make sure that each of our reactants are in the same phase. Because if they're in the same chemical phase, they can now interact better. Okay? Well, what if there's just one of you and there's one of me in this whole world, and I live in another place, Germany? Okay? What's the odds that we're ever going to interact? Very little. Why? The distance between those changed. Well, what if instead of there being one of me, this could make this like a horror story very fast, okay? There were a billion of me. What are the odds you'd interact with me then? Probably higher. Why? The amount of me, the concentration will change the rate at which we interact. Right? So when we think about our rates of reactions, we can tie it back to the relationships that we have with the external world and other people. If we make it more of a, what's the better word for the relationship that you guys are referencing? Which is why you're like, oh my God, I never had a relationship with you.
Romantic?
Romantic relationship, let's try that. Okay. If we look at your odds for finding a romantic relationship, and there's only one person in this world that you could possibly ever interact with or have a romantic relationship with, what are the odds that's ever going to happen? There's one person in this whole
Well,
world.
if there's one person.
What are the odds you're going to encounter that one person?
Yeah, very low.
Very, very low. Okay? But if there's now 500 potential people to have that romantic relationship with, what happens to your odds? They improve. What if there's 40 billion? Your odds go up a lot. Okay? So the amount of things will affect your rate. Okay? This is molarity. Okay? This can also be done with pressure if we're looking at gases. So the concentration of our species makes a big deal. Okay? The nature of the reactant. This is looking at phases. Okay? If you're in one location, but your potential romantic partner, I'm having troubles with words apparently today, is in a different country, there's a barrier to you physically. There's an ocean in between. Right? If your partner's on the other side of this wall, you can't interact with them, at least currently, because there's a wall physically preventing you. The only reason you could get that interaction is if you're in the same phase, the same relationship. Okay? One of the other things that can affect that is surface area, okay? Which doesn't work quite as nicely for relationships, but for chemicals, the larger the chemical is, the more likely it'll interact, because it's big. It interacts with more things. Okay? Mechanism. How does the reaction proceed? Okay? If your mechanism for finding that romantic relationship is going up and say, hey, you want a romantic relationship?
That's your go-to pickup line.
Your mechanism, how you were obtaining that relationship, probably isn't going to work out very well. Okay? But if you change it to come up with some better pickup line than that process, right? You can change the odds for that reaction. How is it occurring? Right? So it's evaluating, again, that concept even back to relationships. Right? When we bring this into chemistry, okay, we talk about collision theory. When we think about relationships, our relationships, you're actually talking with someone, communicating what they physically see, what you physically see. There's all sorts of other variables, okay, that can change the odds for a romantic relationship. In chemistry, our compounds or our molecules don't have a mind of their own. They can't look and say, hey, that's a pretty cool atom. I'm going to go hang out with that atom. It doesn't work that way. Okay? So what's happening with our mechanism or our chemicals is these things are just randomly flying around, okay, and bumping into each other. Okay? This is kind of our collision theory for chemistry. Okay? So one option, if we take a cap off our pen, okay, and then blindly try and cap it, okay, put on gloves so you can't feel which end's which, okay, and try and cap the pen. Okay? You're probably going to have a hard time doing that because you don't have the tools allowing you to be able to see those relationships. Okay? The same thing could go with relationships. This is a really bad example. Okay? Collision theory. This is you finding your potential romantic partner by running around and just running into people. And then being like, hey, how you doing? Yeah.
That's better than
Okay.
the first pickup line.
Hey, how you doing? Or blindly running into people?
Yes.
Yes.
It seems like accidents, so you know. Play that off.
Yeah. Good luck with that. Okay. Temperature. Temperature is an important factor in defining those relationships as well. Okay. Why? What happens as we increase temperature?
The rate increases.
the rate increases. Why would the rate increase? The particles are moving more. Okay? If our particles never move, they can't interact. If we give them enough energy and they move, that we've increased the odds of them impacting each other, which then goes back to affect some of the other aspects within this as well. Because if we have enough energy to cause that interaction, it may not be enough energy to actually cause the reaction to occur. Just because you're running around bumping into people and saying, hey baby, doesn't mean you're going to move forward. Okay? You also have to have the correct energy associated with those attractions. Because if you went through and bulldozed through those people, that's not an accident anymore, and you can't play that off. Right? So you would have to adjust those energy levels to match that chemical reaction. Okay? Catalysts. Okay? Do you have a wingman or woman helping you establish that relationship? Maybe that's why your relationships aren't getting off the ground. You need something else to help out. It's not actually participating in the chemical reaction. Okay? It's not like you go in with your wingman and you leave with the wingman and your potential romantic partner. No judgments. Okay? But that's not what's necessarily happening. It's not getting consumed in the reaction. Okay? Your wingman doesn't burst into a fiery ball of flame when the correct relationship has occurred. Okay? It's not like a fairy godmother. Okay? Helps with the interaction, changes how those reactions or the mechanism proceeds, and increases the odds of it happening. Okay? So that's what we're thinking about with our equilibrium. These are the things that affect our rate, because in equilibrium we're talking about the rate of the reverse and the rate of the forward being equal. All of those things will contribute to that overall reaction. Okay? So equilibrium in acids, why did we talk about it? Okay, well, the whole point was trying to establish what's going on with our reactants and products, and where is the equilibrium for each individual reaction. Okay? So if we happen to look at, the fulcrum was a horrible idea for this one. Let's just ignore this one. Okay? Let's take a look at, say, hydrochloric acid. Okay? What do you know about hydrochloric acid? It's an acid versus acetic acid. It's way stronger. What makes it way stronger? What are both of them producing to become acids? Hydrogen ions. Okay. Which one is the more dangerous one? Well, you said hydrochloric acid. Why is it more dangerous? They're both producing hydrogen ions. Why is hydrochloric more dangerous than acetic? No ideas? It's the amount. The amount of what?
Hydrogen?
The amount of hydrogen. When we look at hydrochloric acid, what happens? Hydrochloric acid turns into H plus and Cl minus. Okay? Notice, what arrow am I showing there? Only a single reaction arrow. I'm not actually showing the other one. That's because if I showed the other one, it's probably something like that. That's in black. And if you zoom in really, really close, that is an actual arrow. Right, what are we saying happens with that? There's virtually no reverse reaction, which means if I look at equal amounts of hydrochloric acid to, say, acetic acid, they will both go to produce H plus and then their conjugate partner. But in the case of acetic acid, our second arrow is significantly larger. What does that end up meaning? The amount of hydrogen ions for acetic acid is tiny in comparison to the amount of hydrogen ions for hydrochloric acid. What does that mean for our equilibrium? Right. If I start with the same size box, and both these cast systems for reactants, okay, for HCl, what happens? I get tons and tons of product. Which of our fulcrums makes the most sense? Left or right? I need tons and tons of product to balance out a very tiny amount of reactant. This ends up being hydrochloric acid. What happens with acetic acid? I need a very tiny amount of product to balance out that amount of reactant. Okay. The end result, whoops. The end result is I can now classify hydrochloric acid as a stronger acid than acetic acid because its equilibrium heavily favors the products, whereas the equilibrium for acetic acid heavily favors the reactants. Depending on where that equilibrium lies, that changes my interpretation about the reactivity of both of those compounds. If I attempted to go through and quantify this, what I can do is to establish the relationships between products and reactants. The more products I have, the smaller the reactants become. In that ratio, what happens to that K value? Would it become very big or very small? If products is large and reactants are small. So if you don't know, let's just guess. Products is 100, reactants is 0.1. What do I get? I would get 1,000. Did I get a bigger number or a smaller number? A bigger number. What happens if my K was the other direction? The amount of products was very, very small and the amount of reactants was very, very large. What happens? I get a smaller relationship. I do that right? I think that's right. Okay. So now what I can do is hopefully have someone gone through and monitored the K values for a bunch of reactions, and I can look at them and use those K values, those numerical quantities, to define whether I have a strong acid or a weak acid. So it can get all sorts of quantified in mathematics, and that gets super exciting if you move into 152. Okay? If you don't, then don't worry about it. Instead, how would we know that we have a strong acid or a weak acid? Okay, well, our strong acids and bases completely ionize in water. These are known as strong electrolytes. This is why you tested those in lab. The weak acids and bases ionize to varying extents. So 151 tends to focus on the strong. Same deal with 130. We look at the strong because it only goes one direction. It only forms products. Right? That makes calculations easier. The weak acids and bases ionize to varying extents. Sometimes we get lots of products, sometimes we don't get a lot of product. Because I now need to quantify where that relationship is, that involves a lot more calculations and thought and all those other things. That's ultimately 152. Are we in 152? No. So how can we establish that relationship? Well, ultimately it becomes memorization. Okay? This is highly encouraged for you to memorize, though not required for this semester. Your strong acids, perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloride, or hydrochloric acid, and then nitric acid. Your strong bases, look for the hydroxide. This goes back to our Arrhenius definition. So lithium hydroxide, calcium hydroxide. Group 1 and 2A cations bound to hydroxides. So anything in the first column and the second column with hydroxide is now defined as a strong acid. All right, well then what is acetic acid? Because we looked at acetic acid, that was HC2H3O2. What is it then? Is that this one? That one? That one? So what is acetic acid? It is a weak acid. By memorizing the strong acids, all you have to do is know that everything that is not one of those strong acids is now by definition weak. All right? We are done. I've got 2 slides left, which we'll finish up on Thursday.